changing now. Things have started changing. People, but is the finances are the real problem for structure.
We are engineers. We always have to push and to tell the people what would be the right way. That's all we can do. So now it's already 5.
Hello. Sir, can we broadcast the event now? It's 5.
Just in a minute or two, you can just broadcast it because Vinay sir is about to join. So we can wait for a minute.
So he has a presidential address. He said he will be leaving at 4:50 and he will be joining back again at 5:15.
Oh, okay. At 5:15, is it? Okay.
Yes.
Then I think let me just connect with our DG whether he's facing any issue.
Yes.
And we can give me a
Okay,
minute.
sir.
Yeah.
Yes.
Sure, sir, sure.
Deepika, he's just connecting only. So once he connects, you can do we can broadcast it.
Okay, sir.
Yeah.
So meanwhile, can we broadcast the event because then the participants will start getting in?
Yeah, that is also fine. You can do so.
I'm just broadcasting.
Yeah.
Hello.
Yeah, Devate sir has joined.
Yes.
Good afternoon,
Good
sir.
evening.
Good afternoon.
Good afternoon.
Good afternoon. Yeah.
Yeah, I think Deepika, we can start now. Yes,
So the participants are like just started coming in.
Okay. So we'll wait for say maximum 3-4 minutes and then we can
Yes.
go on. Yeah.
Just for my information, the questions that will be coming from the participants, they will be coming in the chat box, right?
Yes.
Okay.
In the Q&A session, in the Q&A tab, you will get the Q&A at the bottom. There you will get all the questions.
Hello, Swapnil.
Okay.
Hello.
Sir. Yeah, sir, Deputy sir. Yeah, tell me. Hello. Deputy sir, we can hear you. Hello.
He's
Hello,
not
Swapnil.
here. Now he is.
Yes, we can hear you.
Hello.
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 Hello. Can you hear us?
Swapnil, can you hear me?
Yes, I can hear you.
Okay.
Yeah.
Okay.
So can we start at 5:05? It's 5:04.
Yes.
Okay, sir.
Good evening, everybody.
Good evening.
Good evening.
Good evening.
नमस्कार देवते सर नमस्कार
हाँ नमस्कार भाई नमस्कार
कैसे हैं सर
चलिए शुरू करिए
Okay, so I'm starting the event.
Yeah.
Good evening, everyone. We welcome you all to the IIB lecture series. Today we have with us Mr. George Wolf. He will be speaking on structural bearings and anti-seismic devices state of art. So to begin with the session, I'll first introduce to Mr. Swapnil Joshi, who will be taking care of the session ahead. Mr. Swapnil Joshi is an intellect who possesses bachelor's in civil engineering and double post-graduation from United Kingdom and NICMAR with specialization in construction project management along with law graduation. He has wide exposure in developing systems. He's developed expertise in the field of CPM combining technical and latest management tools such as Primavera, Asta Power Project, Tylos, etc. He initiated and developed a mobile application Nintendo projects for daily monitoring and real data analysis of projects. With successful implementation of digitalized integrated approach and his expertise in project planning, BIM and advanced technologies, he is able to deliver the client goals successfully. Swapnil has been rewarded by Indian Institution of Bridge Engineers from the hands of Shri Nitin Gadkari, Union Minister for Road Transportation, Highways and Shipping in 2014. With this introduction, I would welcome Mr. Swapnil Joshi and hand over the session to him. Thank you.
Thank you, Deepika. Thank you very much. So I officially welcome you all the participants, panelists, speaker for today's special lecture series 11 by Mr. George Wolf on structural bearing and anti-seismic devices, state of art. Now, before going further, let me just quickly introduce about IIB. Rui, can you just go to the next slide of our Director General's introduction? So IIB is founded in 1989, is more than 30 years old organization, having more than 29,000 literature available online, more than 33 centers across India, done multiple international and national conferences, which I think our DG and the President in their speech will give a brief about it. And we have been taking this initiative of special lectures now, which are continuously happening every week or so. This institution is founded by late Sri MC Bideji, and now we are growing in multifolds. And under the guidance of our Director General, Engineer DG Devte, and President Vinay Gupta ji. Now let me quickly introduce our DG, Engineer DG Devte. He's a civil engineer from College of Engineering, Pune in 1974. Through 1975 UPSC exam, he has joined Indian Railways as a class 1 officer and retired as a principal chief engineer of Indian Railways in 2011. During his service, he has worked on many important railway infrastructure projects, occupied important posts of principal chief engineer in North Eastern Railway and South West Railway, director, board member of Konkan Railway Corporation, chief engineer Konkan Railway Project, chief project manager of Tunnel Mumbai-Pune Expressway, project director of Katra to Luli portion of Udhampur, Baramulla JNK Railway Project, and recently he is working as a CGM for first complete fully underground metro construction project for Mumbai Metro Line 3, which is 33.5 kilometers. With this brief, quick introduction, may I invite our DG just to say a few words, and then we can go forward. Over to you, sir. Hello. Hello.
Devte sir, please unmute yourself.
You have to unmute yourself actually.
Okay.
Yeah.
Now it is okay.
Yeah, now it is okay. Please.
Good evening, everybody. I welcome you all for this today's special lecture, 11th lecture in the series. As Swapnil has briefly mentioned, the IIB, Indian Institution of Bridge Engineering, was established in the year 1989 by one renowned civil engineer, Mr. MC Bhide. Because of his bridge engineering background and about 35 years experience in bridge engineering, construction, maintenance, operations, and various aspects of the bridge engineering, he decided to establish this institute, which is exclusively dealing or handling the bridge engineering aspects. Since its inspection in 1989, the IIB started taking keen interest in various subjects and conducted various seminars, workshops, conferences, roundtable discussions, and training programs right from the beginning. And these activities are still continuing with same zeal and enthusiasm. As Swapnil mentioned, IIB has brought out more than 30,000 pages of technical literature and continuing to add furthermore technical papers to its credit. It has 33 state and local centers and more than 7,000 individual members and almost about 170 institutional members, and very active right from the beginning in disseminating the bridge engineering knowledge to all the engineers related to bridge engineering. The mission of IIB is bridging the gaps, that is intercontinental and intracontinental, to building bridges of camaraderie, understanding, friendship, and cooperation amongst engineers, not only in India but of the world, to collect and document all aspects of technology relevant to bridge engineering and disseminate the same up to each and every interested engineer right up to the grassroots level. Now, IIB has organized, after the sad demise of Mr. Bhide, founder of this institution of bridge engineering, the new team took over and continued the activities with same zeal and enthusiasm. We organized 2 days seminar, full-fledged 2 day seminar at Patna. First we organized at Lucknow in 2018. Then in 2019, the seminar was organized at Patna, and 2020, because of COVID situations, we could not organize this seminar, but we organized full-fledged webinar, full-fledged webinar, which was attended by many engineers from all over the country. After that, we continue to have series of technical lectures, and we invited the experts in fields, various fields of the bridge engineering, and which has been attended by all the field engineers as well as students of the engineering colleges, and this series has become quite popular. So we are continuing with this series of lectures. Today is the 11th such lecture, and today's speaker is Mr. George Wolf, and he will be speaking on structural bearings and anti-seismic devices, state of the art. He is expert in bridge bearings. So I welcome him, and with these few words, I welcome all of you for this special lecture. Thank you very much. Thank you.
Thank you, sir. Thank you very much. Ruhi, can you present this, please?
Yes, sir.
So let me now introduce you our second important pillar and the source of energy. Our president, Shri Vinay Gupta ji, he's a director and CEO of Tandon Consultants. He's a civil engineer from Bits Pilani, 1983 batch, and director and CEO of Mrs. Tandon Consultants Private Limited. Specializes in bridges, flyovers, underground and elevated metro structures, precast buildings, 275-meter tall chimneys, etc. He's an active member of various committees like of BIS and IRC. His contribution includes IRC SP65 segmental bridges, IRC SP71 precast pre-tension girder bridges, etc. He's a recipient of many awards from IEI, UKIERI, etc. He has been lecturing as a guest faculty in various institutions like CRRI, CIDC, and many more. He is a India. He's a president, all India president for ICI, and our institution, Indian Institution of Bridge Engineers. So this is he is one of our source of energy to take much more initiative and invite in towards the dissemination of knowledge to the young engineers and to the fraternity. Ruhi, can you go to next? Now, may I introduce our my colleague, Honorary Secretary Dr. Gopal Rai. So he's an PhD holder from IIT Bombay, Chief Executive Officer of the CEO of Dhirendra Group of Companies. Just facing just a moment. His phenomenal level of prowess has enabled him to be associated with several prestigious projects, including the Apsara reactor, BARC, Mumbai Airport Bridge, strengthening of Mithi River, ESIC hospitals, etc. He is an honorary secretary of IIT and general secretary of Association of Structural Rehabilitation and Retrofitting, committee member of ISAC Mumbai Center, BIS and ACI. He has delivered more than 630 presentations, out of which 27 presentations are in the international conference. Also a keynote speaker in 4 international conferences and more than 10 national conferences. Dr. Gopal Rai got the award of 50 Manufacturing Innovative Leaders at World Innovative Congress Award 19. Also in Dubai for 40 most influential leaders under 40 years 2017-18 by Asia 1. So he's my colleague and honorary secretary, gives a lot of inspiration to our young team. Rui, can you go to next slide, please? Now I'm representing a quick representation of a new elected executive committee. We have, stalwarts along with us, and now they're being are a part of the new elected executive committee. So you can see the names. So I'll not deliberate much time on this. I'll go on to the next slide. Ravi, can you just change the slide, please? Now, before wasting any further time, let me introduce today's moderator, Mr. Jitendra Rathod, COO of Sanfield India Limited. He is born in 1979, completed civil engineering in the year 1998, and since then working in the field of expansion joints, bearings and structural protection and monitoring systems. With experience of over 2 decades in these products, serving as a member of Indian Road Congress B Technical Committee, responsible for development and updation of codes and guidelines for expansion joints, bearings, and bridge apparatus. Marathon member of past 9 years. In addition, he is also associated as faculty to various national training institutions like IRICEN and NETI in the past. Also guest faculty on various professional and academic institutions, written technical papers and literatures published in various and international magazines and bulletin. With this brief introduction, may I now hand over the forum to our moderator, Mr. Jitendra Rathod, to take it forward.
Thank you very much, Mr. Joshi. Thanks a lot indeed for your kind words. Before I start with the topic and the introduction of the speaker for today's session, I would like to welcome and introduce to you the panelists that we have for today's session, Mr. S.K. Puri. We are privileged and honored to have him available for today's session, and he kindly consented to be the panelist. Thank you very much, sir. To give you a brief introduction of Mr. Puri, Engineer S.K. Puri, born in 1950. He has done his BTech in civil engineering from IIT Delhi, and then has also done his MTech in structural engineering also from IIT Delhi. And he has a vast experience of over 46 years in the field, out of which alone 42 years is in the field of highways, that comes from both in India as well as from other countries. He has worked in various capacities in different zones as highway and bridge engineers at MORTH, that is Ministry of Road Transport and Highways. And he was promoted to the highest post of Director General, Road Development and Special Secretary. He has also served as member technical for 2 years in NHAI and also as Chief General Manager for 3 years during the period 2005 to 2009. Besides rendering his services to the apex bodies in India, he has also been associated and worked with several governments and highway construction bodies outside the country. To name a few, is the Federal Ministry of Works in Nigeria, where he has been associated since 1991 to 1984. He has also worked as Senior Highway Engineer in Ministry of Communication, Government of Saudi Arabia, Riyadh. He was there associated in the capacity of a specialist for United Nations. Then he has also served for a good tenure with National Transportation Planning and Research Center, Nepal. And likewise, he has a vast experience and expertise, not only from the India, but from the other countries across the world. Currently, Sri S.K. Puri is the president in Intercontinental Consultants and Technocrats, that is the leading consultancy firm in India. He is based out of New Delhi. He is also the vice president of IRC and past secretary of ING-IABSE. And the most importantly, I must emphasize on this point that Sri S.K. Puri is presently the convener of B6 committee of IRC, as well as the member of GSS and BSS committee of IRC. The B6 committee, to be more precise, is the committee in IRC which is responsible for the development and upgradation of the codes related to bridge bearings, anti-seismic devices, and expansion joints. So we welcome you, Mr. Puri, for today's session. Okay, so now moving on with the proceedings of the session, the topic for today's special lecture number 11 of IIBE lecture series, the structural bearings and anti-seismic devices. And the moment this topic comes into the discussions, I must say that the subject bearings has always been a very catchy and a very touchy subject. Why I'm saying so? Because I'm myself associated with this field of engineering and especially with these products for about 22, 24 years so far. And I have never seen any meeting or any forum, let there be any fraternity of people belonging to the client side, maybe the topmost officials like project directors or ENCs, consultants, or even the contractors, and right down to the field officers like site engineers and supervisors. The moment the word bearing comes in discussions, you always find the wide open eyes filled with a lot of curiosity and interest. Oh, is it bearings? Please tell us more about it. And this is for the but obvious reason, because bearings is something which you can say is the most vital element inside any elevated structure. And it would not be wrong if we say that they are sort of lifeline of any bridge structure. So to do the presentation today on this very important subject, we have the privilege of having an international expert with us, Mr. George Wolf. To formally introduce you with Mr. George Wolf, let me take the help of a few slides I am presenting on the screen. Mr. George Wolf, born in the year 1951 in Austria, that's a native to Germany, and he completed his mechanical engineering from Federal Ministry for Technology in Austria, and he is associated with this industry of bridge since the year 1973. So if I'm counting it correctly, it's been already more than 47 years of experience, rich experience that he is carrying with him. In the initial stage of his career, Mr. George has also been associated with academic institutions as the faculty for mechanical engineering as well as business administration with Technical College Austria as well as the Johannes Kepler University. With his all the vast experience and expertise in the field, especially related to bridge bearings, expansion joints, Mr. George is also since quite long time and also currently serving as an expert, as a committee member in various international committees. He is a nominated expert at European Standards Committee, TC 167, which is responsible for bridge bearing standards, and also for Technical Committee 340, which is responsible for seismic devices. He is also a nominated expert at EOTA, that is European Organization for Technical Assessment, and there he is giving his valuable inputs and support for the development of the expansion joints standards. And also he's involved in the Austrian Standards Institute, Committee 14, which is also for the updation of codes related to bridges. Besides this, he is also a nominated expert at ISO, that's the International Organization for Standardization. And there he is dealing with the elastomeric bridge bearings. And he is also a IAPSE as well as a Rotary member. Mr. George, as we all know, he is from Austrian origin, but he is residing in Thailand, precisely in Bangkok since the year 2011. And there he is fulfilling the responsibilities as Vice President of the European Chamber of Commerce, Thailand EABC, Chair of the Working Group for the Rail and Road Infrastructure. So if I have to summarize this, wow, we have with us today the expert going to conduct the presentation who carries an experience of over 47 years under his belt. And this experience covers the academic side, it covers the specification forming, the code development side, as well as the professional experience. So I am very sure we are going to have a good learning through this interaction with Mr. George Wolf. Thank you very much, Mr. George, for joining us and accepting the invitation for becoming the speaker for this session. And now the forum is all yours.
Okay. Okay. We get the screen?
Yeah, you can start projecting a presentation.
Okay, so good evening, everyone, and I'm very happy. Thank you very much for the nice introduction. So I'm going to. Is it okay to see my screen? Yes. Okay. Good.
Yes.
Yes, sir. It is visible. Yeah, you're loud and clear as well. Yeah.
Yeah. Thank you very much for giving me the possibility to show you my point of view about these bearings and anti-seismic devices. So now, I have a little bit of technical problem. Okay. So you see it's opened. Structural bearings. First, let me talk about past and present. The function of the bridge bearings, as everyone will know, is to transmit the loads from the superstructure to the substructure, as well as allowing for thermal movements and rotations due to traffic loads. What are we requiring from the bridge bearing? We require a long lifespan, a high loading capacity, no aging or wear, small reaction forces, and to be inspectable during service. Until the 1960s, mostly steel bearings have been used, roller bearings, rocker bearings, pin bearings, sometimes just lead plates. We see some nice examples here, and we find a lot of them in every country. And we learned a lot of lessons about this in the last decades. The bearings has been widely used, but they have a lot of problems. Mainly is the problem of corrosion. Then we have some problems of rupture due to eccentric loading and wrong design. We have some friction sensitivity to contamination, and we have unfavorable failure behavior. So you see, these are the examples for the corrosion. Especially in many cases, we found a lot of corrosion at the contact lines, which is difficult to see from outside. And it looked not so bad from far away, but in the details then you will see that the bearings are not able to move anymore. The inspection of this zone of the contact is very difficult. You see, you will, I think everyone who is checking bridges has seen already a lot of such examples in his job. In some time, then in some countries, they tried to make stainless steel roller bearings, but as the loads are very high, you need a hardened chromium steel, and this is very big problem because of eccentric loading, when you have a little bit transversal loading, it can very easily happen that the roller is breaking. Another problem we found is the contamination. A lot of the roller bearings couldn't move anymore because a lot of debris and dust came to the roller level, and also we had sometimes people who were painting the bearings much too much. If you see here, you see the paint, and it happens that then the friction went up a lot, and then the bearings were a reason that the bridge had to behave like an arc bridge and not like a flat bridge. Then another problem with those bearings were that in some cases the movement was too much, the roller was rolling out, and then of course it has a very bad behavior, the bridge is going down. So this was the past, and then the modern times started with the laminated elastomeric bearing. This was invented already in 1920 by Mr. Freycinet, but widely used only starting in the 1960s. The bearings are rubber reinforced with the steel plate, where interesting, the bonding in between has no technical function. If you just would take rubber sheets and steel plates, it also would work. The problem would only be that the water can go in a little bit and you have a corrosion. So the bearings enable a movement and a rotation, and of course the load transfer. So here we see when we apply the load, we have a vertical deflection. When we apply the movement, we have a limit in this angle. It should be not more than a tangent of 0.7. And when we have a rotation, we have to put together the influences to check if the bearing can cope with. The bearing is excellent for vertical load transfer and free movement and rotation. The lifespan when the bearing is made of chloroprene or neoprene is very good. The same is today with natural rubbers, which include some anti-aging ingredients. The bearing is very well inspectable and it's easy to exchange. Unfortunately, there are also some disadvantages. What we see, limitation is we cannot transfer very high loads. 15 MPa, that was fine for the low quality of concrete we had some 50, 60 years ago. And we cannot transfer horizontal loads. Of course, you can make a combination with some steel restraints, but then you get again the corrosion problem. And when the movement is increased, the thickness is increased, and this is then also again increasing the vertical deflection. And you know, when I started my job, we designed the bridges only in statical point of view. But today we always more learn that we have to look to the dynamic influence and especially to the fatigue. The biggest problems with this fatigue we are getting at the railway bridges. Then of course the bearings also have aging. These pictures are extreme cases. It looks quite bad, but we have to say frankly, it doesn't change the performance of the bearing. The bearing can still rotate and carry the load and move. It will not break down. So it's the bearing is somewhat friendly to the mistakes. Another problem is the slip out danger, especially in the warm climate. It can be a problem. Some manufacturers, they have some waxes in the mixture, and at some temperature the waxes are coming out and have an effect like a greasing of the surface. This was, let's say, in the 60s, and then in the end of the 60s, 65, in Germany, the pot bearing was developed. And the pot bearing is a steel pot with the rubber disc inside and with a seal here. So the rubber is working like a fluid in a hydraulic cylinder. and you have a piston, and on top, then shortly later, we got the PTFE sliding material, and in the combination, you can make sliding bearings and guided bearings. This was then for a long time the best bearing to have high loads and movements with very low reaction forces, also to low temperatures, and hundreds of thousands of those bearings have been installed worldwide. We can have a much better load transfer, an average around 30 Newton per millimeter square. We have very low reaction forces, also to the rotation. It's a very soft rubber inside, and it was used worldwide all the time. But after some decades, not years, really decades, we found increasing lot of long-term damages of the pot bearings caused by corrosion. The problem is the internal corrosion is invisible from outside, and it's destroying then when the bearing is moving, it destroys the seals in the inside, and sometimes the corrosion is so heavy that it blocks the rotation of the bearing. These are some typical pictures here. You see here this surface here, it should be sliding. It should be like the inside of a hydraulic cylinder, a very smooth and free of corrosion surface. But when you have the corrosion and it's moving, then this surface is getting rough, and it's really destroying the elastomer pad inside. These are the critical points here, this contact surface and the seal below. Of course, when you have a high quality seal, it will take much longer until you get the proper visit. And of course, you also could do something against it in using stainless steel. So since around 8 years in Singapore, for example, only pot bearings made from stainless steel are allowed, but that's really incredibly costly. And still there is the problem that you have no check of the seal. You just can trust when you have stainless steel, you have no corrosion. And on top, we have the PTFE sliding, and here, in the long term, we have seen we get a lot of wear. Especially endangered are here steel bridges, because they have more movement than concrete bridges, and this causes the wear. And of course, also railway bridges. I will come to that later. Yes, and I mean that the PTFE you can check from outside, but the pot itself inside you cannot check. And this is how the damages are looking when the rubber is extruding because the seal is failing, or when the PTFE is extruding. The Deutsche Bahn was the first one who found out a lot of damages. They own 25,800 railway bridges and dismantled over 200 pot bearings. They lifted the bridge, take out the bearing, opened it, and then they found out 1/3 was no longer functional. The age of the bearings was between 20 and 40 years, something like that. It was the process went until the end of the 1990. So in 2005, they blacklisted the pot bearings. And in the USA, AREMA, which is the standard for the railway, also blacklisted the pot bearings. But in many countries, it's still used a lot. Let's look to the PTFE, also called Teflon. It was developed in the 1950s, polytetrafluoroethylene, and it was the only long-term material transferring high loads with low friction. First used for the bridges in the 60s, it became widely used worldwide. The negative long-term effects of creep and wear were neglected, and there was no real alternative. When we look to the tests, you see here we have a PTFE test with 45 megapascal for 20,000 meter accumulated slide parts. And we have to say the PTFE is not looking good, but it's still alive. And 20,000 meter is a very high number. On the right side here, we see a test of a non-dimpled PTFE. Here, normally the PTFE has the dimples with the fat, with the initial greasing and lubrication, but in the guides you use it without the dimples, and this is already after 2,000 meters, it's heavily worn out. The problem is when the PTFE, you know, the thickness over the recess is only something like 4 millimeter maximum. And if the 4 millimeter wear away, then it touches steel to steel, and then suddenly the resistance to the movement is jumping up. And the problem is it's not very well visible. You really have to inspect quite often to find it. And if the PTFE is overloaded, which can happen also very easily due to rotation with eccentrical forces, then you have a long-term creep, which is more or less not stopping. It's like you have a dove for the noodle and you squeeze it and it's going out. Yeah. Okay, then to avoid the problem with the pot sealing, in a lot of countries they changed to spherical bearings with the PTFE because at least you can check the PTFE from outside. And it was working quite okay, but this type of bearing was more costly than the pot bearing, about, I would say, 25%. But very large such spherical bearings have been installed. You see a picture here. Then we had another development in Canada in the 80s. The disc bearing was developed. The disc bearing is a polyurethane disc which has a center hole for a shear pin and which can be combined with the PTFE sliding parts on top. The vertical forces are transferred and the polyurethane disc allows the rotation. The horizontal forces are transferred by this bolt in the middle, and the movable bearings get the PTFE sliding element on the top, as you see it here. And this is a very low-cost bearing and became very popular. Here you see they have some rings outside to hold the urethane in the case of a problem. But this bearing makes a lot of problems. It has significant disadvantages. The resistance to the rotation is very high. You know, this disc is not as soft as the rubber. It has a big, you need a big force to rotate, and that gives eccentric loading to the PTFE, and then the PTFE is wearing out much quicker. And this bolt in the middle, which is transferring all the horizontal forces, is a subject to fatigue and to corrosion, and it cannot be checked from outside. So when you have sudden horizontal loads, e.g. for a railway bridge you have emergency braking, or in a road bridge you have an accident on the bridge, then it can happen that the bolt is breaking suddenly and you have no more safety for the horizontal forces. You see, this is always covered, it's invisible, And this was the reason in Europe this bearing was never used. And the European bearing standard EN 1337 is now in revision since some time, as you see here, since this is from 2013. And in the new version, there will be a warning where they say these bearings designed with internal restraint for horizontal loads are not recommended for bridges, as inspections of the element vital for the transfer of the horizontal load is not possible. The use of bearings where load-bearing elements subject to wear, corrosion, aging, or fatigue are not inspectable in service should be avoided. This is really, I think, the only really dangerous bearing. So when the central bolt fails, it can look like that. I mean, this is just an eye catcher. I don't know really the reason of this falling down of a deck in China. Oops, sorry, I was a bit too quick now. So then 1969, Germany developed the magnetic levation train, Transrapid, which is today in service in Shanghai between the airport and the city. And there was a test track. And in this test track, there have been the PTFE bearings installed. And within a short period of some months, the bearings were destroyed because the train causes a very small movement with a very high frequency, like a sewing machine, and the PTFE couldn't cope that. It has an incredible wear. So in the time of this development, then in about 1995, some bearing manufacturers in Europe, they joined together for a search of better materials, and they found ultra-high molecular weight polyethylene, UHMWPE, and developed and the material and tested different formulations, and finally got in 2002 a European technical approval for it. And this material has a lot of advantages. It was a kind of a technological breakthrough in terms of service life, because with this material you can transfer much higher loads with a low friction, and you have no wear and no creep. The material is absolutely resilient and undestroyable. It has no aging effects. It has a lifespan like stainless steel. So we found, since we know the material, not any change of the material if you are in the load limits of these approvals or even further. The material itself has been used over 40 years as a successful biomaterial for use in artificial hips or knees and spine implants in the clinical use. But this has a white color, and the special thing for the bearing is it's a mixture in the material with some ingredients which are, how to say, not disclosed to the public. So with this material, there was a 50,000 meter test, and you know this test was running for incredibly long time at a temperature pattern where the temperature changed from -30 to +45 degrees. And when you look to this material after this incredible test, you see it has no wear. It just has some marks from the scars from the movement, but it's still like new, and you could make another 50,000 meter, but that would be too costly. The test was running at the University of Stuttgart, and it was very expensive. Below you see the undimpled material which is used for the guides, and here also with a test with a high load of 50 megapascal. After 10,000 meters, nothing, nowhere is visible. If we compare, if we go back again to the PTV, then it's very obvious which big difference is here. So this material can be used in the spherical bearings. You can have the rotation with this material. You can have the sliding movement and also the guides with the material. So when you compare now 3 designs of the bearings, you see the high load capacity. You see for a vertical load of 10 meganewton, the rubber bearing will have a diameter of around 920 millimeter. The pod bearing will be around 650, and the ultra high molecular weight polyethylene disc will have only 400 millimeter. So this is also going very well with the use of the ultra high strength concrete, which is getting always more. And also, of course, when the bearing is much smaller, it's also cheaper. It has a lower price. The prototype testing lasted 3 years. The limits for the loads and the temperature, aging, environment, and wear of the material were researched by these official test institutes with very high efforts. And you see here a picture of the 50,000 meter sliding. Here's 45, 60. And that was then the basis for granting the approvals. So first the name was ETA, European Technical Approval, and then there was a change in the European Union's laws, and they changed the name to assessment. So 5 manufacturers got such ETAs for this material, and it's also very successfully produced in India already. Now, in the last 2 decades, many thousands of such bearings have been installed worldwide. And then there are some details which still needed improvement because the basic steel parts, they have a corrosion protection, but for the callot, it's very difficult. You cannot make a very thick paint under the material, and so in the first bearings it was a chromium plating, but that was not so. You know, we mean this bearing has the same lifespan as a structure, so it may be 100 years, and the people had some doubts about the corrosion, and so today it's state of the art to produce this part, the callot, from a corrosion-resistant material like a stainless steel or aluminum alloy. Yeah. Some references for those types of bearings is, for example, the very famous Millau viaduct in France, or in India, in Delhi, for this Wazirabad bridge. Under the pylon, there are 2 giant such bearings for 231,000 kilonewton. You see the picture here, and they have been fabricated in India at Sandfield under the eyes of Mr. Jitendra. And another thing, in Thailand, up to today, we installed nearly 10,000 such bearings. Only in one project, Red Line, we installed 4,712 such spherical bearings, and they were all made in India. So that's a very good reason. We have to talk here about the temperature, because all those sliding materials, the PTFE and also the HMWPE, are plastics, thermoplastics. They are sensitive to the temperature. The PTFE can be used between -35 and +48 degree. I mean, this is the temperature of the standard and of the test. Of course, you can use Teflon for much higher temperature. I mean, in your kitchen, you will have some pans with the Teflon, and you can heat them up to 300 degree. But the tests for the sliding materials was just in this range. And the characteristic compressive strength is 90 megapascal up to 30 degree, and then it goes down, and at 48 degree as this limit, it's still 57 megapascal. But the ultra high molecular weight polyethylene can be used between -50 and 48 degree in the first generation, the first tests. But some short time ago, I think around 6 years, there was a second generation developed. It's called MSM Plus, and here you can even use it up to 80 degrees Celsius. With a characteristic strength of 180 MPa. You compare that's double what you have in the PTFE, and at 80 degree it's reduced, but it still carries 75 megapascal. And this system for seismic load even can take a compressive strength of 240 megapascal. So that's really a big step. But maybe you say, why do I use such high temperatures? You know, we have to plan the bridges for 100 years in advance, and we don't know the development of the climate. Here you see the climate, the world temperature development between 1880 and 2020, and you see it's going up. I mean, it's not so much, is 2 degrees. But another problem is in the civil engineer standards, mostly they consider only the shadow temperatures of the past. And the bridges are mostly exposed to direct sunlight. I personally have seen big problems, for example, when the asphalt was applied to a steel bridge, you know, that asphalt had a temperature of nearly 200 degrees when it was put on the decks, and it warmed up the decks like crazy. So the bridges are exposed to direct sunlight, then sometimes you have a black asphalt on it, and you need a provision for the future. So from my point of view, in the warm countries, like the most parts of India, you would have to consider at least something like plus 60 degrees to be on the safe side. Okay, so the next I would like to say something about railway bridge bearings. You know, a road bridge and a railway bridge is very different in terms of the requirements for the bearings. How come? It is because the railway bridge always have the same spots. The train is braking on the same spots. The train is accelerating the same spots. Then the weight of the trains, especially locomotives, is very heavy, and the structure themselves are mostly more lightweight. So if you see here, you see the bending under the load from the train, and here I got some data about the let's say to compare the road bridge and the rail bridge. You see the rail bridge are the red spots and the road bridges are the blue, and here is the rotation in radians, and you see that the railway bridges go much more up than the road bridges. The biggest problem are long span steel bridges here. And these cycling moving loads, so many trains passing the bridge every day with the higher amplitude compared to the roads, they cause a rotation at the bearing point. So a lot of the road bridges, you cannot find any real rotation due to the traffic load at the bearing. But when you look to the railway bridge, in nearly all cases, you can measure the rotation when the train is passing. There is a big interaction between the deck and the track. And that's, you have to always to imagine the rail has to go through and is connected with the deck. And that's not the same in the road bridge. You have the expansion joints, and if it's a little bit bumpy there, it's not so bad. But if you have problems with the rotation of the railway bridge, then you bring a lot of additional stress to the rails, and that can make big problems. So up to now in the standards, we don't find any hints for railway bridges, but in the next revision of the European standard EN 1337, there will be an informative annex which describes in detail what you have to take care when you select the bearing design for the railway bridge. Are some things like the arrangement of the bearings. You have the vertical deck displacement. And if you use the elastomeric bearings, they act like a spring. That's the same for the elastomeric bearing and also for the disc bearing. And this causes a permanent fatigue stress for the rail. It's very small, but every time the train is passing, you have a deflection of some small number, and this makes an influence, especially for it's very difficult for the high-speed trains because they don't have the ballast. When you have a ballast on the railway bridge, it is a small problem because the ballast will equalize these movements of the deck. You will just have more maintenance of the ballast because it's then a little bit like a stone mill. But when you have a slab deck with the slab track, then it's really very bad when you have a deflection. So you need a stiff bearing. Otherwise, it goes to the stress can lead fatigue cracks under the surface or completely. Or I know a bridge here in Thailand where every 8 years they have to exchange all these clamps because they are breaking because of fatigue. And they should change the bearing. This is a vertical displacement, but we also have problems with horizontal displacement. We found some bridges for the railway where they were designed with a floating arrangement on elastomer bearings, and that works because it works. Why? Because the rail itself is holding the bridge in position and is transferring the horizontal forces. But that's not what the rail is designed for. It's not calculated to hold the bridge. And there is sometimes no good communication between the engineers which are responsible for the bridges and the other engineers which are responsible for the train system and the track. That's an international problem. Then we have a vertical, another problem. In some cases we found the bearing is much too far away from the end of the deck, and then the rotation will cause a gap on the surface. If it is a straight bridge, this is only a minor problem, but if it's a railway bridge, also this again is causing additional stress to the rails themselves. Similar problems occur when you have an inclined bridge deck, when you have a slope, and the bearing is installed horizontally. That's the old rules say the bearings always should be horizontal, but that's not good if it's a movable bearing. If you have an inclined bridge and the bridge is moving, you get a step here between these points. And this is, of course, not good for at the road bridge for the expansion joints, but it's completely unacceptable for railway bridges. So in the where the people listen to me, I convinced them to install the movable bearings for the railway bridges in the slope. Normally the slope of railway bridges is very small and it's not really a problem. You just get a little bit more force on the fixed bearing. But then you have a smooth movement and no stress on the rail. Oh, sorry, it was a bit too quick. Okay. Yes. So I'm sure you're also interested about the cost of the bearings. So from my experience, in average, the cost of the bearings is only between 0.9 and 1.3% of the bridge building budget. And then when you look to the different types and you say the traditional PTV pod sliding bearing will be 100%, then the rubber bearing is much cheaper, it's only 50%, but it needs more place, of course. The disc bearing is also cheaper. The PTV sphere bearing is a little bit more expensive, but, and this is the good news, the modern bearing with the long lifespan is cheaper than the traditional solution because the size is smaller. Yeah. In the design of the bearings, in some cases, we also have uplifts, especially for skewed bridges, and such uplift devices are very often designed in form of such clamps. But when this is designed, we have to learn that there is no standard covering these uplift things. The standards, I would say, are anyhow not a cooking recipe. We still need engineers. We still have to switch on the brain. We have to think a little bit and not only follow the standards blindly. And I have seen many such uplift clamps with incorrect design. The vertical play has to be very limited, smaller than the recess of the sliding material. Otherwise, the sliding material can be kind of sticking to the surface of the stainless sliding steel. And when you lift it up, then it goes out of the recess and it will not come back in the right position. And also the clamps must work in the rotated position of the bearing, so it must have a curved contact surface. And in a lot of cases, this was missing. For short-term uplift, it's a good solution. If you have a long-term permanent uplift, which in rare cases can occur, then you also need a sliding element in these uplift clamps, or you need a special design of the bearing. But you should always take into the mind that such things shall still be inspectable all the time from outside. In some cases, we have to exchange old bearings, and sometimes there's not so much space. So there's also development of a spherical segment bearing, which is also covered by ETA. And here you can install a bearing instead of, for example, a roller bearing very easily with the same advantages. Another thing for the exchange of the bearing, there is very often a problem to connect the bearings on top to the bridge because the dowels from the old time are on a different space. And so we have a very good development here because there was in the last decades, there were a lot of progress with bridge strengthening by means of steel or CFPR lamellas. And for this purpose, there were bonding agents and bonding processes developed also with ETAs. And with the same materials, you can bond the bearings to the deck. We just have such a case in Singapore where they have to remove a lot of old pot bearings, and the new spherical bearings are bonded on top to the deck. And then it's no problem at all to take horizontal forces up to 30% of the vertical loads. I shown here a sample of such a bonding material. Of course, it's not only Sika, there are a lot of companies having this approval already. So this was first part, and now maybe some words for the standards of the bridge bearings. In Europe, we have the European Standard 1337 structural bearings, and we have this European technical assessments or approval, and both are based on the Eurocode. It's a system together. And in the US, which is used also a lot in many countries, we have the AASHTO for the road, we have the AREMA for the rail, and we have ASTM for some materials. The development of the European Standard 1337 started in '89, and I joined the committee in 1990. And before, there were some national standards like British standard and German DIN standards, but many countries had no standard at all. And the development of this standard run in parallel with the development of the Eurocodes, the year 1990 series, which is covering all the building codes. And this was quite a little bit complicated because many of the drafts made in the committees were rejected because of the system change of the Eurocode. The Eurocode followed a very different philosophy than the standards before, and the new approach had to be introduced also in the bearing standard. The first part of this standard was then published in 1997, and the last of the, in total, 11 parts in 2008. And now, since a long time, since I think 7-8 years, a revision of this standard is underway. The standards shows this in 1337, the state of the art from the 90s. It's very, very detailed. It has 410 pages in total, and it's the only international structural bearing standard. And now there are efforts to publish it as an ISO instead of only European standard. The standard, it contains a very complex quality system that includes a permanent control by third parties. So there are special independent institutes. They need an accreditation from the European Union, and it's traceable on the internet. So you can look to the type plate of a bearing, and there you see the number of the third party inspector, and you can in the internet see in a table from the European Union if this contract is of surveillance is still valid. And for developments outside the range of the standard, as for example now for this new sliding material, the ETA is required. But the ETA issued by IOTA is always strictly following the standard as far as applicable. So it can be sure that the ETA quality and the the bearing according to standard quality is the same. In both cases, you can get a CE marking, which is then the official sign that all the requirements are met. And this is really guaranteeing the highest quality and lifespan. Because, you know, the European standards are issued by CEN, Center of European Standardization, and not only the now 27 EU member states are there a member, but the CEN has 34 member states. They include the countries like the UK after Brexit, Switzerland, Norway, Turkey. But any country can join CEN, and any manufacturer worldwide can apply for CE mark contract and ETA. So the system is not limited to Europe, and is widely used outside of Europe. And the special thing is the Eurocode always allows to introduce the national requirements. They have so-called boxed values. They suggest some values, but it can be regulated in a different way when the national requirement is different. A very good example is a temperature range. And the ETA system allows it to be always up to date and permanently learn from actual development. If a product has an ETA and it turned out later there are problems which not have been covered, then the ETA will be withdrawn, of course. So now when we look to the AASHTO, AREMA, the United States, they have a very different understanding, a different philosophy. They have no standard for the bearings. They have a bridge design code, one for the roads, and one is included in the manual for railway engineering. So the AASHTO has only a chapter about the bearings, and this is some, I don't know, some 50 pages, so it doesn't cover a lot of the details. And some materials are then covered by ASTM codes, but special materials like, for example, the seal for the bearing, for the pod bearing, is not really well described there. The standard then in America always say the engineer has to decide, but the problem will be that the engineer of an actual project may not have the experience. So in fact, the bridge designer and the bearing supplier have to consider many things which are not stated in the standard. And also the quality system is very different. The US has the philosophy that the supplier is responsible, and we also make some load tests. The supplier, they say, we have 10 years warranty on the bearing, so when a problem happens, the supplier has to change the bearing. But this is not covering when the problems happen 20, 30 or 40 years later. And the load tests, I mean, I'm so long in this business, I never have seen any bearing which didn't pass the load tests. And it's not a real problem. And the European system makes a very difficult prototype testing and then the permanent third-party checks. And I remember very well the time before this was used, and we had so many damages, and then the number of the long-term damages is really declined very much dramatically. Okay, that was what I wanted to say about the bearings. Now a short words about the anti-seismic devices. So for the anti-seismic devices, we have a European standard 15,129. The latest edition is from 2018. And this is based on the Eurocode 8, design of structures for earthquake resistant. And you see there are a lot of different types listed. For the bridges, we have 3 different tasks. We have a restraint system where we want to protect by load distribution. That means, let's say, the bearing has to take the additional force of the earthquake. Then we have isolators, which are protected by basic isolation and also have an energy dissipation. You see a principle sketch here. And then we have dampers, which are mainly for energy dissipation. This is also an example here. we have the restraint systems. We use the bearing itself, but we add the horizontal force from the earthquake there and have a bigger restraining ring or guides, or we can have shock transmission units which are free movable for the slow movement, like coming from thermal expansion. But when the seismic shock comes, they are stiff and they can transfer then the horizontal load to the abutment, and so that the piers are not heavily loaded. For the isolators, we have different designs. One is an elastomeric bearing, so you have a kind of a regular elastomeric bearing, but it's a special mixture which has high damping properties, or you can have a lead core inside. Yeah. This again, of course, it's difficult to check once it is installed. But these things are widely used in anti-seismic. And then you can have the sliders as an isolator. That means that helps you that there is no load from the earthquake transferred to, let's say, a pier head. And here we have two designs. The one is a slider like here. This is nothing else than a free spherical bearing. But you can use here special recipe for the plastic material, so that you have also limited transfer and energy dissipation. And the second model is here. You see you have the curved surface on both sides. This has the advantage of a recentering, and it's also energy dissipating, because when the horizontal force comes, it moves, and a part of the energy is changed to heat. For the damping, we have the hydraulic dampers, which work in the same way like the shock transmitters, but this can be also a semi-active type. In this type, the liquid inside these cylinders is a magnetorheological fluid. That means you can, by electrical loading, you can influence the quality of the fluid inside, and so you can make it very stiff or very soft to get the effect you wanted for the damping. And then you also have different kinds of steel hysteresis dampers, which are working with plastic deformation of steel parts. You see it here. Finally, I would like to show you a sample. This is a viaduct in Spain for high-speed railway systems, 1,220 meter deck length with 19 piers, up to 92 meter height, and the train makes a braking force of 7,600 kilonewton, and the load on sliding isolators is 25,000 kilonewton. Here you have this part of the bridges are longitudinal isolated, and this part should take the load of the earthquake with recentering fixed bearings. That's the schedule here. And here on the end, you also have the dampers. This is pictures of the damping bearings, and here you see installation of such a damper at the end. So this was what I wanted to show you today. I thank you very much for your attention. I'm happy to get some questions now, but if you want further questions or you want the PDF copy of the slides, you can always contact me with my email address or in the LinkedIn. Thank you.
Thank you very much, Mr. George. It was indeed an excellent presentation, and really fascinating as how you have took us through the various bearing systems, what has been followed in the past, and what is the practice now, and what shall be the vision for the future. You have also given us a very good insight about the international specifications. As the questions are coming in, I request all the participants that if they have any questions about the presentation or anything related to the topic, they can post their questions in the Q&A section, and we will be taking up the questions in a short while. And by the time the questions are coming in, may I take this opportunity to go to our panelist, Sri S.K. Puri, to present his views about the presentation and what he thinks about this topic. Mr. Puri?
Thank you, Mr. Rathore. I think, as you have said, it was an excellent presentation by Mr. George Wolf. He has taken us in the history, right from the history, when roller rocker and pin bearings, and going into the neoprene bearings, and coming to ultimately the spherical bearings. What interesting point, the takeaway I would like to take from here is, and maybe all the other delegates who are listening to it, it is what we are facing. I can share the experience of our committee in India when we are working in, improving our standards. We do follow European code, uh, Eurocode, and not the ASHTO in this particular bearing case. Like it has said that Mr. George has clarified that the responsibility lies only on the manufacturer and not the design part, or the guidelines are missing. It is the material in the spherical, the cost of the bearing for a structure, it has been said 0.9% to 1.25%. And within the cost of different kind of bearings, I would say it is hardly 0.3 or 0.4% of the structure. So it obviously comes to that it being one of the vital component of the bridge. And since a maintenance and inspection of bearings in a bridge is a very difficult and very costly affair, and normally it is ignored, it is very important that the bearings, we should try to have the bearings which last for the life of the structure, unless otherwise in a special case if something is to be done.
So I think I made a mistake because I forgot to say how much it costs to exchange the bearing.
Okay.
The original price is not so much, but when you have to exchange the bearing, this will cost a lot. It can go up to 10% of the original investment. Yes.
Yeah, correct. So I was only coming to the original part of the bearing when
exactly. But I forgot maybe in my presentation to explain this. And also maybe another time I can make a presentation to you about bridge inspection. Yeah? Because there also in Europe we have very good progress with the modern sensor systems, which is a low-cost method and very precisely to make general checks of the bridges. That's a very interesting thing. I introduced that also in Thailand, and I don't know myself if it's already used in India.
Mr. Wolf, you raised, or rather you indicated a very interesting feed for us. Would you be kind enough to deliver a lecture on this bridge inspection, which is another field which lacks a lot in India, except for railways, where Mr. R.K. Goyal is involved. In other disciplines and highway disciplines and all that, it lacks. So you think...
Just not this year, huh?
Yeah, sure.
Okay, agreed. We'll remember it for the next year. But next year starts on the 1st January, keep in mind.
Yeah.
So thank you, Mr. George, for clarifying. So what I was trying to point out is that in our experience, we have seen a lot of damage to the bearings, and I would only the takeaway from you is from you, this lecture is very important, that the cost of bearings as compared to the cost of structure is very small, and we must try our best not to go in for cheap kind of material or cheap kind of bearing for reducing the cost of the bearing. And like you said, that this new material of UHMWPE, which is much better than PTFE, which is to be used in the spherical bearings.
Yeah.
And we in India also, in our course, we are, discussing these issues. Already we have mentioned. Only thing is that in India, we are still having some kind of challenges for testing of these material and bearings, which we think that we are trying to sort it out, and so that these bearings can be used extensively in future in bridges, because as you said that this material can be compared with stainless steel or aluminum alloy. So
Yeah.
that means it has the life equivalent to the life of the bearing metal itself. Because
Sure.
any, yeah, sorry, you wanted to say.
The life of the structure.
Yeah, correct. Same thing. So normally we are designing a structure for 100 years and bearing should last that. So what now we are talking is that the inside material, the sliding material within the spherical bearing, that should also have that life. Now that is what is important, which is coming out in your this lecture. And we do agree, we do have that exposure, and we are also in India trying to work out that, slightly having challenges for the inspection or testing of these kind of material and bearings.
Yeah.
But thank you very much to give that specific. In fact, another thing which you have said, which we were frankly not aware of, that the disc bearing, which we were also thinking, but the disadvantages you have pointed out, I think
Yeah.
that disc bearing, then there is no future for these disc bearings.
No, it's very dangerous.
If it is so dangerous, because in a bridge structure, there is never a sudden collapse of any element of the bridge. It gives you a lot of warning that you can take some kind of a corrective measure, whether it to the extent of external pre-stressing,
Yeah, yeah.
removing of expansion joints, all those things. But if the disc bearing has a, it collapses, that means it can be a fatal, which you have
We
given.
can, we can compare it with the cables of the state cable bridge. You see the picture behind me.
Yeah,
There we also had a very bad experience in Europe because we had the cables which were mantled with a plastic or with a concrete even, and inside you had the heavy corrosion, you had the fatigue, and you didn't check it from outside. Impossible. We have now the method to check it, and second, we know what to avoid. We have to make designs which are inspectable, yeah, and exchangeable.
nice. Thank you very much. So I am taking from this lecture is, and which we will deliberate in our IRC meetings and B6 committee of this,
Yeah,
is that the best possible bearing is the spherical bearing, as of now, what we know.
at the
And
moment, yes.
the only limitation is the sliding material in this. So we have to have some kind of more research improvements to improve that material, so that we can have long life of bearings, wherein we can have very limited maintenance and inspection, because
Yeah.
that practically we have seen. In fact, after my government service for the last 10 years, I am working on the field itself in various bridges, and I find that routine inspection is not done anywhere in the world, in the bridges or structures. So whatever failure happens, the bearing slowly, whether it's corrosion or it is shifting or sliding, and within months or years, it really collapses, and then replacement of bearing is a big job. It's a really a difficult and tedious job. So
Exactly.
with that feedback, I'll give back to Mr. Jitendra Rathore, our moderator. Thank you very much.
Thank you very much, Mr. Puri. Thanks a lot for your valuable words. And since we are also to keep an eye on the questions that are pouring in, may I take in the time a few questions, and then we have other panelists and other delegates also joined, and they can also, I will go to them as much as possible for their views. Mr. George, there is a question coming in from Mr. Sukalyan Sarkar, and he's asking what is the maximum distance at which a bearing should be kept from support in case of bridges in order to keep the vertical inclination of the deck within limit at support so that there is no bump created at the surface.
Now, yeah, I mean, this is a very simple geometrical calculation. When you have a slope and the bearing is moving horizontal, yes, you can easily calculate what is how many millimeter of height difference you will get, and then you have to check what is okay for my system. So when the result is very small, some millimeters, and you have a rope bridge, then it's no problem. But when it would be a large difference and it's a railway bridge without ballast, it will be a problem. It's very easy to calculate, I think. This.
Yeah, that is very right. Yeah, and
Not moving like this, but like.
and just to
There is no
yeah,
fixed
that is right.
number, there's
And
no mathematics. It is really, you have to work out by a simple mathematics and
Yes.
see how much it is deflecting upward through the inclination and the curvature and the inclination finally at the far end, and see what you would like to tolerate, but there's no codal value. So there is no such thing.
Exactly.
May I add,
that is right.
Yes,
may
sir.
I add, this is simple dispersion. Take the load dispersion to 45-degree angle, and it should be within the thickness of the structure. That's all. Simple.
Right.
There is another question from Mr. Gautam Jha, and he wants to ask if the elastomeric bearing lose its contact from the bottom surface, then how it is going to affect and what can be the consequences of it.
Yes, it depends. You have to look what is the reason for the losing of the contact. Sometimes you have a rotation, and then the elastomeric bearing is lifting a leg. Yes, you can push a piece of paper under the bearing, but in fact that looks a little bit strange, but it's not so bad. It's only negative when the bearing then is moving and is slipping out. The bearings are not slipping out 100%, only partly. But when you see it at the bridge inspection, you should check up the bridge and push the bearing back. That would be a first easy step. It's not the elastomeric bearings are very easy. It's not really such a big problem, but you shouldn't use it for the real large bridges. Yeah.
Jitendra,
Okay.
can I comment on this?
Yeah, I was just in fact waiting to come to you, Mr. Goel.
Just for this question.
Yeah, please go on, sir.
Yeah, actually, one has to explore the reason why the steel plate should lose contact from the support. Actually, quite often, people are not centralizing the bearing with respect to the mean temperature, and that is creating all the problems. So the question posed by Mr. Jha is basically a kind of signal. One has to go into the details why this is happening, and in all probability, I am sure they will find that it has not been properly centralized. But
Yeah,
of course,
maybe.
the site has to be seen.
Yeah, you have to find the reason, and then you have to think, can I tolerate it, or do I need a different solutions? But in the most cases, finally, you can tolerate it. It's not really dangerous. That's what I want to say. It's a different way. For example, the roller bearing, the roller is already looking like it will roll out.
No,
That's,
it is actually, sir, placement of the bearing initially at the right spot.
yeah, exactly.
Yeah, that's right. That's right. Yes, yes, yes. There is another question, sir. It's a little bit complicated question that you have covered in your presentation that for a certain load capacity, the size of the spherical bearings equipped with UHMWP could be very small. But in India, the practice we used to follow, we are designing the bearings and limiting the size of the bearings by the capacity of the adjoining concrete structure or steel structure permissible stresses. But as much as I understood and read about the European codes, you are first designing the bearings and then you are nominating the maximum possible pressure or stresses that can be transferred from the bearing to the structure. And then the structure interface is designed suitably, maybe with concrete alone or with high strength epoxies to take up that high stresses. So, what is your opinion as an expert between the two approaches? There is a difference between the two approaches followed worldwide and followed in India.
So, I mean, when you have a high load and you have a regular reinforced concrete, you can look in the Euro code, and you will find when you have enough edge distance and the good reinforcement, you can have a pressure under the bearing up to 3 times the characteristic strength of the concrete. Yes.
Okay.
Because the characteristic strength of the concrete is taken by a sample which is not reinforced and which has no edge distance. Yeah? That's the one thing. The other thing is, if you really worry that you cannot have this edge distance or something, then you can have a simple steel plate to distribute the load from the bearing. That's a very cheap and easy method. In Thailand, we have a lot of the precast element bridges, and you can easily cast in a steel plate to distribute the load. Yeah, but you can have the advantage of the small bearing. Of course, you also can enlarge the bearing. You can say, I specify, I don't want to have more than, I don't know, under the bearing. That's the method.
Yeah, that's right. That's right. It is very good to see that many people are showing in the interest and the questions are still pouring in. But due to the paucity of the time, we may not be able to take all the questions, but I'll just try to take maybe 1 or 2 more questions. Mr. Harshvardhan Subbarao wants to say something.
York, thanks for that
We can
excellent
take
talk.
one more question and then we can have the discussion, Mr. Subbarao, if you allow. I can just take one more question.
Okay.
Why? Because this question may change the mood of the session. It's an interesting question. As Mr. Gaurav Bhai wants to ask, why not to eliminate the bearings because it is one of the weak portion of the bridge, and instead of it, use of integral bridges altogether?
That's a very good question. I wanted to. No reason. It's not funny. It's a very good question. I wanted to integrate it in my presentation, but I was limited with the time a little bit. And you know, it is no question, no bearing is the best bearing. And when you look to the old bridges from the Romans, which are 1,000 years old, they have no bearings. But you have to put an arc bridge, for example, to accommodate that. And I investigated once a big arc bridge in Germany, and between 6 in the morning and noon time, the peak of the bridge moved up 12 centimeters, okay? So you cannot use this, for example, for a high-speed railway. And then the arc bridge is very, very much more expensive than the type of design we are using for ordinary bridges. So the integral bridge for sure makes sense, but only in a limited case, because you have one big danger. If the integral bridge is getting wrong, and you get the cracks and you get the problems with the internal corrosion, then the cost of repairing that will be incredibly high. And you know, when you build the integral bridge, and the most people are, I don't know why, but they're forgetting it, you not only have to calculate the minimum requirement on the structural elements, but you have to limit the upper, because in some cases, you know, you have a steel which is stronger than specified, or you have a concrete which is stronger. And then you have a very different behavior. You have different stiffness than you expect. So this is also something in the seismic design, you know, you have to think on what happens if it goes wrong, yes? The behavior, where is the point of the rupture, what is breaking? And this is the big problem for the integral bridges. If it's a small bridge, it's a frame, I think it's a good solution. But when it goes for spans more than, let's say, from my experience, 20, 30 meter, it's a dangerous play with the fire if you look to a 100-year lifespan.
Yes. Thank you very much, Mr. George. And I'm sorry, Mr. Subbarao, for stopping you, because that question was so tempting, I could not resist from asking. Please go ahead, sir.
Yeah, Jörg, thanks for that wonderful talk. It's opened up our minds to quite a few things. One point that comes to mind is we're trying to develop this code for extradose and cable stay bridges and the articulation of the needle bearing, as we call it, or the needle beam. It utilizes 8 bearings on each side. It's typically a box at the interface, which replaces the so-called plunger bearings of the past, the hinging at the center point of 2 opposite spans. So this needle bearing typically employs 8 bearings on the beam on each side. So if it's a box, you have one on that side and one on this side to take out torsion. Now, the issue here is if we design bearings with 100 years guaranteed life, that is equal to the service life of the bridge, design service life of the bridge. There is no need to replace these bearings. Then this is an ideal solution. In fact, we are thinking of condemning these solutions, but this in effect will become an ideal solution provided you make a stainless steel beam or a very long life type of coating for the steel needle beam itself. And we have bearings which are 100 years capacity, 100 years guaranteed service life.
Yeah. Okay.
It won't need replacement.
Yeah. Can I make the comment? This is a very, let's say, a question which was developed at the start of this material. My point of view is you always have to take care for exchange of the bearing, but you have a different. When you have a PTFE bearing and you know this will work only 25 years, then I have to exchange it. Then you have to make a design with an easy and cheap exchange. You need some space for your checks, and you can check up and do it out and exchange. But when you have a bearing like this ultra high molecular weight polyurethane, it's a terrible name. Then you can take into account a more costly method to exchange. You know, it's like with temporary piers. Yes. So, for example, for Thailand, we developed a concept. They have very long elevated highways where they don't need the places for the jacks anymore, but they have a steel construction where I can lift up the deck. And this steel construction can be taken for many spans. Yes. So you'll save a lot of money with that.
But not over water. Over water, we wouldn't be able to do that over long crossings.
Of course, over water, you have to make a system. You have to think which system can I have. But you always have to have the possibility to exchange the bearing, even when the predicted lifespan is so long, because you never know, it can be a mistake happen, shit happens everywhere. Huh? It can be a mistake, it can be a...
But again, the point is when this needle bearing system was evolved some years ago, they were using pot PTFE bearings in the concept. Now the fact that if we can shift to smaller, longer life bearings, a smaller bearing is easy to take in and take out.
Exactly.
So if we limit the size, then this becomes a viable concept. And the beam itself can be made easily to withstand 100 years. Steel withstands 100 years, stainless steel withstands 100 years with ease.
Exactly, that's exactly the point. The bearing is much smaller, so the cost for the design to make it exchangeable is also much smaller.
And what would be the cost?
Yeah, just to add to...
The pot to bearing is a multiplier of how much cost? Say, how much is the cost multiplier between the pot PTFE and the second generation spherical bearing?
Yeah, I said from my experience...
It's about 10%, I think, more. As I remember, 1.1 and 0.9 are the two factors Mrs. George gave.
This becomes a very viable system to adopt for our long Exodus bridge crossings.
The bearing is, in any case, cheaper than the old pot sliding bearing.
Right.
Cheaper.
Right.
Also, the plastic material is cheaper than the PTFE.
There you go.
You know, I have been reading a question about the patent, but the patent is finished. Huh? The bearing is, the design is already 20 years old, and there are a lot of different mixtures, you know, with the same basic, but there are a lot of manufacturers developing materials, and so it's not a problem. Every bearing manufacturer can get a license from someone who developed such a material. That's not so limited anymore. That was 10 years ago, it was a problem.
Right.
Thanks
so much.
Only one manufacturer, you know, that was...
Yeah, I think Mr. Alok, thank you very much, Mr. Subbarao. And I think Mr. Alok Bhomik wants to have something. Yes, sir, please.
Yeah, first of all, congratulations, Mr. George, for such a fascinating presentation. I must say, you have covered in your presentation practically the state of the art in bearings, from elastomeric bearing to pot PTFE and even the seismic devices. I think it was an excellent presentation highlighting the pros and cons of various types, and it was very useful. Couple of points which I just wanted to sort of clarify or give my observation. Number one, in my view, it is not that spherical bearing is the solution or panacea to all problems and solution to all types of bridges. Depending upon the nature of load, the span arrangement, the span length, and the type of structure, every bearing has got its own niche where it is suitable. So in my view, all the type of bearings has got its applicability. It depends on what is the vertical load, what is the horizontal load, what kind of structure, whether it is a highway or railway, as very correctly put by Mr. George. Second part which I wanted to mention is that we are talking about increasing the design life of bearings, which is absolutely true, which is very much required. But this is no substitute to replacement of bearing.
Yes, yes.
You can never think, I mean, ultimately we have to think of bearings which are replaceable. If you provide a bearing, it has to be of replaceable type.
Yeah, it can never be fail-safe, Alok. It can never be a fail-safe system. Yeah.
Right. It can never be a fail-safe system.
That's what I just said.
Yeah. And the most important point, which Mr. George very rightly pointed out, is that the cost of bearing is only 0.9 to 1.3% of the total cost. And somehow or the other, the procurement system that we adopt, we ultimately go for a system of procurement where there is a cutthroat design optimization done by the bearing manufacturers. And that is something which if we can avoid by changing the procurement system, because ultimately in the overall cost, the bearing cost is insignificant. But if you really see the kind of cutthroat competition in which we are in. Once you give the vertical load, people are talking of saving 2 millimeter, 3 millimeter in the thickness and competing with each other. And that has a sort of little bit of detrimental impact on the performance. I think something needs to be thought about it.
Okay.
And
So,
last point,
the
performance of the bearing not only depends on the design. Design is only one aspect. The installation and the maintenance are two key parameters which many failures we have seen in bearing because of the bad installation, poor arrangement of the bearing, and poor maintenance. I think these are also issues. I wish Mr. George can give one more presentation highlighting the manufacture, installation, and maintenance problems with the bearings. Thank you.
Very good. So that was 4 questions, huh? The first is different bearings for different purposes. I'm sorry, I know so many different bridge designs, but I only know 2 bearings which are really working. The one is the rubber bearing, and the second is the spherical bearing with this material. I don't know any other bearing which can give you performance for different bridge design. The rubber bearing is very good, but it has some limitations. And the spherical bearing is for all others. Then the second one, replaceable, of course, I said before, you're fully right. You have to have the possibility to replace the bearing, and as you said in your first part, especially mistake at the installation are very common, okay? The next part, you said the procurement, and this the manufacturers try to make it cheaper. But okay, you have to have a checklist for the verification of the bearing. When you follow the standards and the ETAs, it's very, very, very detailed. And no one can cheat on this. Of course, I know cases where, for example, a supplier had a very nice calculation and drawing, but what he delivered is very different. So you need someone who has a little bit of knowledge for the inspection of the materials. And regarding the installation, so in the European standard, you have a very good example for a form for the report on the installation. You need skilled people in the revision, which is planned from the European standard. You have a kind of like a license for installing the bearing. You have to make a seminar to learn. You have to get something like a driving license for the bearing installation, okay? And maintenance, you can forget it, because the modern bearing doesn't need any maintenance, not the rubber bearing and not the spherical bearing. If a bearing needs maintenance, it means it has a wear, a aging, or another problem. Yes, so we don't have that anymore. And
thank you very much, sir.
Yeah. Sorry. That's the answer.
Okay. I think we are already shooting beyond the time. I'm sorry. The discussion is very interesting, but we have to somewhere also keep an eye on the watch. But Engineer Ravindra Kumar Goyal, I think he is having one question for quite a long time. Sir, I'm sorry, but I have to ask you to be quick as much as possible. You can ask your question. That should be the last question we can take.
Thank you. Thank you, Jiten. Actually, my question is regarding the STU that you have covered as seismic restraining device, shock transmission unit.
Yes.
I just want to know, as you know, railways are having old bridges which have been designed for a limiting longitudinal force. And now we are having high horsepower locomotives, long haul trains, and they need to exert high longitudinal forces. So I just want to know, has you or your organization has ever tried to use these STUs to take care of this excessive longitudinal forces on the bridge substructures in railways?
I would say this is the typical use of the STU.
Yeah.
It's a very classic use of to strengthen the bridges, and with the STU to avoid, I need strengthening the piers or something, yes? And of course, we have to take into account that the train is also distributing the horizontal forces with the track. Yes.
Yes.
So the distribution is really difficult. And I think today you would solve such things with a finite element calculation only. Then you have a good method to see all these influences coming together. In the past, without such an instrument, it's not easy. Huh?
My question is, has it been used somewhere in the past in some of the railway bridges elsewhere outside India? In India, I know it has not been tried. But if there is an experience of doing it somewhere in the rest of the world, then probably we can learn from that and then we can implement in the railways.
So, you know, I know a German company who is producing these STUs, and they are working, they are the owners of Sandfield, so Mr. Rattore can ask them in Germany for such references.
Okay.
Sure, sir. I can share with you the references of such projects where STUs have been used for retrofitting of railways for improving the traction load capacity. Yeah. So thank you very much, sir. Thank you all.
Just 10 seconds more. Actually, the problems of maintenance of bearings, as has been said by Engineer Puri also, that in road authorities, they are not inspecting the bearings. So my suggestion is all these problems of maintenance can be taken care of if we go for annual maintenance contract or the initial procurement contract with AMC of the lifetime. So that way the life cycle costing can be compared, and that will take care of the possible replacement frequency of the bearing if there is any.
Yeah,
I think that can be an idea.
That's a great question because it gives me the possibility to answer it in my next presentation about the bridge inspection.
So we are looking forward to your presentation, and you have to give us a date, please.
Thank you.
Okay.
Thank you, sir. Thank you very much for all your questions. And I would now request our president, Mr. Vinay Gupta, to maybe have a few closing remarks before we get on to the further proceedings of this session.
Thank you, Mr. Rathore. Nothing technical. I will only speak about a little bit more about IB, I would say. First of all, friends, especially those who are the participants, maybe I don't see them. COVID-19, challenges and opportunities. Challenges, I think we all know very well. Opportunities, we know little. But if you look at it, people are joining the forum from all over the country, from all over the world even. We are able to get Mr. George Wolf kind of people. If you ask him to travel to India, he would think 10 times. But since it's on a video platform, we really have a distinct advantage of having excellent speakers and excellent presenters, and of course, the delegates. So that is the advantage we are taking. And therefore, we had this every fortnight event, which is a series of special lectures. Today, we are on the 11th. Wherein we focus on a very small part of the bridge, but we go into details of it. If I just talk about like bridge in general, yes, it's a good topic. But when you talk of a bearing or an expansion joint, there is so much of intricacy involved in each of these disciplines. And of course, we rightly have the convener of the Bridge Bearing Code Committee, Mr. S.K. Puri. So that makes, of course, a difference to all of us. But friends, in bridges, and bridges are public structures, we all know they stand in front and you see them, public sees them, the media looks at them, and the politicians look at them. So safety is extremely important. I must say that there are 3 S's: strength, speed, and safety, which is extremely important. We learn, in fact, more from failures than from success. So if you have done this learning, we have done part of our job very right. There are always failures. You call it bearings, you call it concrete, you call it pre-stressing. There are failures. They may not necessarily meet or rather result into catastrophe or result into casualties. But failures are there, small or big. And we learn from those and say, okay, I'll do this next time. Like Mr. Wolf said that what is that? Elastomeric bearing is good in certain circumstances, but not in every circumstance. Or he said that the disc bearing is no good, but the disc bearings have been provided. Only then people learned there are some problems. It's like, vaccine we are developing. We have done all the trials and everything, and still we are finding that after giving the first practical vaccine commercially, there is some problem. And we learn from those problems. So that's how we go about it. Uh, of course, you rightly said that needle bearings, like Dr. Harshvardhan said, they do require the hinge beam or whatever we call it, they do require a set of 16 bearings. So we cannot get away from bearings. We have to use bearings. They are an integral part of our bridge, whether the bridge is integral or not. Let us say you have an integral bridge and you have a short pier. If you have a short pier, the forces on the pier, the locked in forces on account of creep, shrinkage, etc., and temperature, they become so high that the whole thing is not designable. Even the pier is not designable, foundation is not designable. In those, the solution cases, the solution is bearings. Or sometimes we reduce the forces by putting a pi type of structure, wherein you have integral in the middle and piers have the bearings. So solution does not lie in eliminating bearings. Solution lies in improving the bearings. We cannot give up. We have to live with it. We have to find ways and means. Yes, one thing very rightly Mr. Alok Bhaumik said that why are we so concerned about the cost of this bearing? It's only some 0.8 to 1% or 1.3%. But how to find a procurement mechanism to buy a bearing or get a bearing which performs well is where people like Mr. S.K. Puri or somebody has to do some R&D to find ways and means of contracting that we get a fantastic bearing. Lastly, friends, I'd like to first of all thank our inspirational power, Engineer D.G. Devte, the Director General. It's not a vote of thanks. I'm just from my heart only, I'm trying to thank a few people who I know they have been absolute inspiration. And of course, all the panelists we have here. Then we have this two high profile workers, I call them. They are workforce. Engineer Swapnil Joshi, Honorary Secretary, and then Dr. Gopal Rai, another secretary, Honorary Secretary. And there are some backstage workers. You don't see them much. There is Miss Ruhi Agrawal and there is Miss Deepika Singh. They are available more like 24/7. I send a message, I get a reply to the message even, leave aside phone call, and the job is done. Only then this kind of event can be put together to come up, take a shape. So I think with these words, I will thank everybody, and I will now request Ms. Swapnil Joshi to carry forward with the proceedings. Yes, Swapnil. So what next?
Yeah, now next is we would like to invite our Honorary Secretary, Dr. Gopal Rai, to propose a vote of thanks. Gopal, over to you.
Thank you, Swapnil, and Gupta ji, बहुत बहुत धन्यवाद. And let me like बहुत दिनों के बाद एक शायरी बोलने का मन किया है कि.
So George, there is some poetry. Please don't mind us in Hindi.
I think Swapnil will convert it to English. I will explain the meaning is, although the bearing is very small thing, but it decides the future of any bridge. I will summarize in English. Absolutely. But in Hindi, it छोटा सा बेरिंग सही न लगा हो तो बहुत कुछ दिखा देता है. छोटा सा बेरिंग दिखाई नहीं देता है, लेकिन सही न लगा हो तो बहुत कुछ दिखा देता है. So with this note, we should be very serious about, although whether it is 1%, 99 plus 1%, or after installation it might become 1% will govern 99%. So we should all. And let me thanks to Wolf for giving fantastic present. It is like we have gone to bearings. Even if engineering, we get few authors or few speakers who start from scratch and they reach up to the capstone of mountain. So that's a part. So really thanks, and we look for next year, means another 20 days after that we came, and we look for it with the new message. structural audit and all, because that is for the day. Thank you very much for today's speaker, Engineer George Wolf. Thanks to today's panelist, Engineer S. Sir, for giving a very conclusive remark and also comparing the Indian scenario and the international counterpart and taking India into another milestone for the bearings and coordinations. Then let me thanks to today's moderator. Really fantastic. I think there is a big round of clap to Jitendra Rathod ji. Fantastic thing. I thought I'm looking at some like news and comparing and all that. How best you've done, how best you have handled the time and everything, and your expertise on the bearing is known to whole Asia. In the field you are working with Seinfeld, fantastic, really, and really it is a new addition to the bearing and expansion joint. Thank you.
Thank you, sir. Thank you.
Engineer
Thank you, sir.
Goyal ji from Indian.
Thank you. Thank you.
Yeah, let me thanks to Dr. Harshvardhan Subbarao, Engineer Alok Bhomik ji, Swapnil Joshi ji, Vinay Gupta ji, and President our DG Dute sir, and my colleague Deepika and Ruhi. Thank you very much for all your support. I don't know how much percent involvement I am there, although Vinay Gupta ji told me that big worker, but I don't think I'm eligible for worker also. So with this note, and I say thanks to all IIB team, all the panelists, all the delegates, and all the upcoming speakers. And I don't know, this is opportunity. Wish you a grand success new year. Okay, to all the speakers and delegates. We'll have more lectures, but to our today's speaker, a grand success and healthy new year to Engineer Wolf. Any concluding work from Engineer George Wolf?
No, just thank you very much and goodbye and see you next year.
See you. Very happy New Year in the meantime.
Thank you all.
Okay.
Okay.
Happy New Year to everybody. Happy New Year to everybody.
Everybody.
Happy New Year. Thank you.
Happy New Year to everybody.
Thank you.
Thank you.
Thank you.
Thank you, Ms. Rohit. Thank you, Ms. Deepika, for all your support. Thanks a lot. Thank you.
Thank you.